Hey, what's going on, everybody? It's Derek, and we are back for week 6, where we're going to be bringing the concepts of AWS architecture and high availability into the picture. As you can see, we're also going to do a quick summary of the networking section that we did last week. But it's important to know, especially because this test in particular is for a solutions architect. It's important to know a little bit about AWS architecture, right? And some best practices and services that help kind of support a decoupled architecture, which should pretty much always be your goal. So that's what we're going to go over today. It is a little longer, so I've got a lot of coffee and water on standby. Hopefully, you do too. If not, maybe pause me, go get it, and we will get going here. So, to sum up, or to recap networking again, rather, remember that the virtual private cloud, VPC, is basically where all of your resources are going to live. It's the main component of AWS networking. It's a logically isolated section of the cloud for deploying resources. It requires a CIDR IP block upon creation, so something like 10.0.0.0/16. It has or is made up of subnets which segment your VPC into multiple networks, and you can have public or private subnets, and each of them exists in one availability zone, but you can have a subnet in multiple availability zones, or I should say you can have subnets in multiple availability zones rather. Okay. So again, subnet could contain like an EC2 instance, maybe as a public one, and then maybe a private one would contain like a database instance, something along those lines. Security groups offer security at the instance level. They have allow rules only for inbound and outbound, and they are stateful, meaning that if, for example, a request is allowed to come into your EC2 instance, then it's going to allow that traffic to just inherently go back out as a response. Okay. NACLs, network access control lists, offer security at the subnet level, right? So network access control lists work with subnets at the network level. They offer allow and deny rules, unlike security groups, which only offer allow rules. And they're stateless, which means that just because something is allowed in doesn't necessarily mean that it's going to be allowed back out as well. Okay. Internet gateways are basically what allow you to have access out to the internet for your public subnets. Of course, you don't want private subnets having internet access. And then a NAT gateway is, in that case, what allows your private resources to go and access the internet if that is required. Okay? So, virtual private networks are what secures a private connection between your VPC and your on-premise resources. And it requires a virtual gateway, which is going to sit in your VPC in AWS, and a customer gateway, which is going to sit in your on-prem data center. And then upon setup, you need to configure endpoints and routing, set up route tables, and remember that the connection has to be initiated from the customer gateway. Okay. Direct Connect is kind of like plugging in that Ethernet cable. It uses physical infrastructure to keep your traffic off the public internet and provide a direct link to your AWS resources. And it offers very high speed and connectivity to AWS, just like an Ethernet cord would provide very high speed and connectivity. Okay. VPC endpoints. Currently, there are two primary endpoints that you'll want to remember. There are interface endpoints, which are used to connect pretty much any AWS service via something called the AWS Private Link. And then there's gateway endpoints, which are, as of now, only used to connect to S3 and or DynamoDB, okay? Elastic IP addresses are what are used to provide a persistent public IP address, and they can be attached to an EC2 instance or an Elastic Network interface, okay? You can detach and reattach these EIPs between different instances, and then because they are allocated to your account, you will pay for them if they are not being used and attached to an instance, okay? So as long as you have them, you're going to pay for them. Elastic network interfaces are virtual network cards that attach to instances. They can be moved between instances to kind of create sort of a management network if you have a use case for that. And then elastic network adapters provide enhanced networking features for much faster performance. And they only are supported on very specific instance types. If I remember, it's the instances that are compatible with like Nitro technology, which is kind of a new hardware that AWS is implementing. I haven't worked with it much yet, but those are ENAs. So, Route 53 is the managed and scalable DNS service that provides secure and reliable routing of requests. So, of course, DNS is domain name service, and it basically kind of translates, website names into IP addresses or vice versa. And you can specify multiple routing policies. So you can have simple routing policies, which randomly send requests to an IP address in a pool of IPs you have configured. It does not offer health checks, though, which is important to note. You can have weighted routing policies, which define a percentage of traffic that you want going to each resource associated with a single domain name. So if you had two instances, you could say you want 60% going to this one, 40% going to this one, for example. You can do geolocation policies, so that's where you route users to specific resources based on where that user request comes from geographically. And then geoproximity is similar, except that it also considers where your resources are located on top of where the user request came from. So it'll kind of match those two up. But it needs to use Route 53 traffic flow, which is something extra you kind of have to configure. And failover policies, which route traffic just to a different resource if an original one is unhealthy. Latency policies, which route traffic to a region with the lowest latency for an end user, so whatever's closest to them geographically, with the lowest latency is, I should say, whatever is closest to them geographically is probably going to have the lowest latency. And then multi-value lets you return multiple values, for example, IP addresses, to a DNS query. And it's really useful if, for example, you want to make sure the resource that you're connected to is healthy. Right? And then Amazon CloudFront is a fault-tolerant and globally scalable content delivery service. So it uses cached data at edge locations via distributions for static and dynamic content. So, for example, if you had S3 as your data source hosting a static website, you could additionally add origin access identity OAI to secure that S3 data source. Okay? You can define which locations your data should be distributed to provide your end users with the lowest possible latency. So that's kind of the goal of CloudFront is reduce latency for your end users for frequently accessed data. Okay. All right. AWS and high availability. So high availability is very important, for cloud computing in general because it's one of the big sells of cloud computing, and that if something were to happen to a particular piece of hardware, you could easily have another one ready to go, so your applications continue to remain available. Right? So let's go ahead and jump right in here. So everything fails all the time. This is a quote from Werner Vogels, who at one point was the CTO of AWS or Amazon. And I'm not sure if he still is, but he was a big deal in the company at one point, and he's the one who said this, not me. Okay. But because of this, high availability is one of the key value propositions of using the cloud. So it's important to understand what it is, how it's implemented, and what options you have. And if for no other reason, you're going to have multiple questions on the test that ask you, specifically about which of these solutions would maybe provide the highest availability. Okay, so keep that in mind. Some workloads definitely need to be more available than others. So, for example, if you have like a production workload that's business critical, that needs to be available pretty much all the time versus just like a testing environment that you're playing around with. And then AWS provides high availability by physically linking data centers in an availability zone together with high-speed cables. Okay, And then high availability generally comes with higher costs for your business because you're provisioning more resources just in case something happens. All right, so we got some pictures coming up. So don't, some of this is a little abstracted, but, we'll throw in some visuals here and hopefully it'll make more sense here shortly. But two kind of very important things you want to remember are RTO and RPO. So RTO is your recovery time objective. And this is basically, the maximum amount of time your service or business can be down without incurring significant financial losses. Okay. So, for example, say you have a company and you can only afford to have your production environment down for a maximum of 15 minutes because, after that point, you'll start losing track of transactions, you'll start having poor end user experiences, and maybe they'll go somewhere else, whatever. Okay. So, that one's a little more straightforward. But RPO is slightly more confusing. But it's basically the max amount of time or maximum amount of acceptable data loss measured in time that you can incur without significant financial harm to your business. And it sounds a little confusing, but think of it like this. Think of it like you have an enterprise level company versus a small business. Okay. For that enterprise level company, 15 minutes of downtime is going to lose a ton more transactions than maybe a small business that doesn't really get that many transactions. Okay. So when you're thinking of RPO, it's more related to data loss, but it's measured in time because over a certain point in time, you're going to have a certain amount of transactions. So RTO is directly related to time, and then RPO is related to data, but it's measured in time. Okay, so hopefully that makes sense because I've definitely seen questions before about RPO and RTO. Okay, so some of the best practices for defining your RTO and RPO are to measure each of your applications and environments independently because they're all going to have different requirements. So, for example, a production versus a test environment, like I was kind of alluding to earlier, they're going to have vastly different requirements because they have vastly different impacts on your business. Okay. So kind of understand the difference between your different environments and kind of how they contribute overall to your business. Okay. So you should be asking open-ended questions to determine what sort of impact a disaster is going to have on your business. Questions such as if one of our applications are lost for an extended period of time, what are the repercussions, right? Financially, reputationally, or otherwise. What is the estimated cost of a loss in regards to both financials and reputation, as I just kind of alluded to? What does your SLA dictate in regards to your application's availability for customers? So if your SLA says, hey, our application is going to be available 99.95% of the time, then having an incident that brings your availability down to 98% violates that SLA, and you could have some problems. Does an application act as a dependency for others? Right. So if this application of yours fails, does it bring other things down as well? And are there any regulatory requirements stating how quickly the app needs to be back up and running? So maybe you work in financials or healthcare and you need to have things up by a certain amount of time if a disaster were to happen. Okay. And by answering these questions, you'll have a better idea kind of how long you can afford an outage, right? So it kind of helps you brainstorm a little bit, but you know, this is something that's more kind of on the business end because having problems and outages impacts your business, right? We're not just like setting this up to say, oh, cool, look at these computers and whatever we got set up. No, everything serves a purpose, right? We're trying to, make businesses more efficient, help them make more money, and provide better services. Okay. So, this is going to be our first graphic we're going to look at before we take our first break here. So there are four common recovery strategies that you can consider, and it really depends on two things. Okay, number one, how much money you want to spend, planning for disaster recovery situations, and number two, how long does it need to be between when something happens and when you're back up and running as expected? How long in time can you afford to be down? So from left to right, what we're going to do is we're going to go from slowest to recovery, like longest recovery time, but the cheapest. And then on the right, we have the most expensive, but it's pretty much no downtime at all at any point, okay? So on the right, we've got our backup and restore, okay? And the RPO and RTO can be expected to be hours. It's for lower priority use cases. You basically restore your data after something happens, and then you redeploy resources after something happens. And it's cheap because basically all you're doing is you're storing your data. You're not creating extra copies of resources. You're not doing anything extra aside from storing all of your data. So if your entire physical architecture were to just explode, you would have all your data backed up elsewhere, but you would have to redesign your architecture, redeploy everything, reconnect everything, reconfigure everything, but you have your data. Okay, so it's cheap, but it takes hours potentially. All right, so that's maybe best for like a test environment that's not critical to the business. Yeah. So next you have the pilot light recovery strategy, which has an RPO and RTO of like tens of minutes, so maybe 10, maybe 20, maybe 30 minutes, something like that. It's slightly less stringent RTO and RPO, so again, it's going to be definitely faster than backup and restore. And it's basically what it looks like is you're running extremely scaled down versions of your core services, and you just kind of have them like provisioned but not started. Okay, they're just there. They're ready to be started and scaled up after something happens, and you do need to go to that. Um, but you're still backing up your data, of course. But you're also, again, kind of ahead of time provisioning just a few kind of key services that your business would need, but you're not necessarily using them or anything like that. Okay, they're just ready to go if needed. All right. Then you have a warm standby with the RPO or RTO of minutes, so maybe just a few minutes as opposed to like 20 or 30, something like that. It's got a more stringent RTO and RPO, so this is maybe kind of starting to get into the production workloads where you really need your stuff to be back up ASAP if something happens. So business critical services. It's kind of the same idea as the pilot light, except you're probably going to have a few more resources actually running. But again, they're just more scaled down versions. They're not necessarily like production sized workloads. But they're still running. Okay, that's kind of the difference between pilot light and warm standby. Is that in warm standby, your business critical services are running, but at a smaller scale, and then pilot light is you just have like maybe one or two core services. And they're not really even running. They're not designed to be used in any way, shape, or form. They're just designed to be there so you can scale them more quickly. Okay? But a warm standby, theoretically, you could use these business critical services if you wanted to, but that's not really the point of it there. Okay, the point is to have them running, and then you just scale them up after something happens. Okay, but because you do have things running kind of around the clock, ready to go, it's going to cost you more money. All right. And finally, you have the multi-site active, which is when you can tolerate pretty much no downtime with like no data loss, and it's got RPO and RTO of real time. So if something happens, you probably won't even notice. Okay, it's so pretty much everything that your business, your application needs to run as expected according to your SLAs and your business requirements. It's running in multiple places. And because of that, obviously, you basically like doubling or tripling your architecture's cost because you're running mirrored copies of it in multiple kind of availability zones or maybe even multiple regions. Okay, so those are definitely something you'll want to kind of know off the top of your head. And AWS has great documentation that goes into more details about those if you want to kind of go down that rabbit hole. But I think that's good. That'll get you there because I like pictures. So hopefully this is helpful. But let's go ahead and take our first like 4 or 5 minute break here. And we'll come back and we'll carry on. All right. So, moving on from our disaster recovery strategies here, we're going to take a look. So, here's kind of what we went over during the actual graphic. So, if you want to kind of run through and just kind of do like a quick high level summary of what we talked about here, then there you go. So, we'll just kind of pass through that since we already went over this. So, we're going to kind of reference this slide here, let's call it a little bit, as we continue to move through here. But kind of the point of this whole thing is to show you that you've got multiple VPCs that are in multiple regions, so that alone makes things highly available. And then you've got different availability zones connected with different kind of copies of your backup. So let's kind of take a look at like some more granular details of backup and availability strategies. So if we kind of thumb through here real quick, you can see that things are changing just a little bit. But essentially, what we're doing here is we're looking at different disaster recovery strategies. So if we come back to here to our first one, what you're going to see here is that you've got in this first availability zone, you've got a instance that's using an EBS volume, and there's also a RDS instance here. Okay, so the RDS instance is being backed up via snapshots, which are being stored into S3. Okay, and our instance is running a file system as well that's being backed up through AWS backup. And then our EBS volume, of course, we're taking snapshots of that and backing it up to S3 as well. Okay, so that is the essentially how we would be backing up these resources here. Okay, but what we're also doing to increase availability and resiliency of our data is we're taking a cross-region backup here. Okay, so we're saying, all right, we want to take this data that we're storing in these, 3 places here, and we also want to store it over in this different region in this separate VPC. So if heaven forbid something were to happen here to this VP, just this whole region, then we would still, have the potential here to restore over here. Okay, so what this is saying for our next step, right, backup and restore, is we could take this data that's stored in S3 and backup, and we could restore it to its rightful place, let's call it. So these would be our backup resources that we would create at some point, which aren't created now because this is backup and restore. But if we had something happen, we could restore our EBS volume that was over here from our snapshot to a new one. Same thing, we could restore our file system, and then we could restore our database. Okay, and again, if something were to happen to this region, we could just do it all in this region. Okay, so all our data is here, and it's the same thing, right? We would just restore our EBS volume, restore our instance, restore our database. Okay, so that is a little bit more of backup and restore visualized. So hopefully that helps you just kind of see visually how things would kind of work in a backup and restores strategy. Okay. All right. So the pilot light here. As you can see right here, you've got your active kind of architecture in this VPC. But then you've got this other kind of setup here that is inactive, for this production traffic. It's in a different region. It's got an identical setup, right? So you can see these things are grayed out because they're not really running, they're not scaled up, they're not ready to go. They're just there just in case we need them. We could switch our kind of production workloads over to this new region. Okay. So we've got a web app here, and we get requests maybe out here from the internet, and it hits our Route 53 DNS resolver, comes in here, hits our load balancer, and then that pushes it to one or the other of our front end servers, which then takes it to our application server, which then do whatever it does to our primary database. And we also have a replica here that, since it's on Aurora, they're going to be pretty much up to speed with data consistency. But we can also, to support this different region over here, we can do cross-region replication from Aurora over here to this live database. So this database is ready to go, right? This is one of our core services. We need our data. And heaven forbid something were to happen to this region, we could then just turn on these front end servers, turn on these application servers. And since we already have a load balancer in place with a route from Route 53 pointed to it, once we just activate this, we could then scale it up and it would be our new production workload, which has all of our data, because we would then just switch this replica to be, the primary database. Okay, so that is kind of what a pilot light recovery strategy would look like. And then if we have our warm standby, it's kind of the same thing. So you can see that it's still inactive here. We're not necessarily forwarding traffic over here. But we have got, some of our servers here turned on. So basically what this means is it's kind of the exact same scenario. And say something were to happen to this region. Now, instead of having to turn on all 4 servers, all right, so we can see back here, all 4 of these are inactive. We already have 2 active. So it's going to take theoretically half the time to get this up and running, because we only have to spin up these 2 servers, right? So we can immediately get these 2 accepting traffic, scaling them up, while these kind of provision over here and then scale up to the necessary requirements to meet the demand as well. We're still replicating data to this database. But again, the key here is that we have 2 servers kind of already running. They're very scaled down versions of what these production servers are going to be. But we're not sending traffic over here either, right? But we are running these to make sure that we have a faster start if we do need to go over here and recover from an incident. But again, because we're running these, these 2 servers here, it's going to cost a little bit more than if, like here in the pilot light, they're not actually running. Okay. Now, multi-site, active. So this is just mirror images of each other, right? So, in this case, we have a DynamoDB server instead of our Aurora database, for example, and we've got these DynamoDB global tables, which are automatically replicating. So all data is the same. We're backing up within each region, so we've got multiple backups. We've got multiple scaled out production servers here. We are actively routing to each region, so this is costing a lot of money. But if anything were to happen to this region, you would probably never know, because it'll just immediately route requests over to this region instead, which already has a fully scaled out set of servers and databases. So that's going to be your active recovery strategy visualized. So hopefully between the 4 of these, you can kind of understand the ins and outs of each disaster recovery strategy and in which situation each of them could be helpful, okay? All right, so back to the slides here. Let me grab a sip. That was a lot. I know it's a lot, but the more you see it, the more familiar you will become with it, okay? So high availability and fault tolerance both have the same goal of keeping your services up and running. They just use a slightly different approach to achieve that end goal, okay? The key difference between fault tolerance and high availability is this, okay? A fault tolerant environment has no service interruption, but it has a significantly higher cost, while a highly available environment has a minimal service interruption. Okay, so again, a fault-tolerant environment has no service interruption, but a significantly higher cost, while a highly available environment has a minimal service interruption. Okay, so fault-tolerant has no interruption, highly available has minimal, something can happen, but it's going to be back pretty quickly. Okay, so high availability can be thought of as meeting SLAs using your system as a whole, while fault tolerance can be thought of as how you keep your resources running despite failures. So again, high availability, think of, you have an SLA that your application is going to be available 99.95% of the time, okay? So that's not 100%, but it's very available because it's available 99.95% of the time. But fault tolerance is again going to focus more on keeping everything running despite failures, right? So it's a little confusing, but that's kind of the key difference there is that high availability kind of helps you to meet SLAs and it means minimal service interruption, while fault tolerance, focuses more on no service interruption for your actual resources. Okay. All right. So AWS storage gateway for on-premise backup. So if you're backing up your data, which a lot of businesses should be and probably are, you're gonna consider utilizing the cloud. You know when you do that, you can help back up many of your on-premise resources as well in a few different ways. So you don't have to store everything on premise. You can use the cloud to store stuff as well. And many companies actually do this. They have what's called a hybrid architecture, right? So they have some resources in AWS in the cloud, and they've got some resources, over here on-prem in their own data center. Okay, but you have three types of gateways that you can utilize to kind of connect the two and make them kind of complement each other. So you've got a file gateway, which works off of NFS protocol, and it securely stores your files as objects in S3. And it's basically going to mimic a NFS, so network file share, to mount or map drives to a bucket. Okay, you've got a storage gateway which uses iSCSI base protocol, and there's two different types of volumes you can have within a storage gateway, and you'll definitely be asked about them at least once, so get familiar. But you've got a stored volume, which is going to be the local storage, or your cache is going to be backed up to S3, but your primary data is still going to be stored on premise for low latency access. All right. And then you've got a cached volume, which caches the most frequently accessed data on premise, but it's going to use AWS and S3 as the primary data storage. Okay. So stored volume, kind of the key differences here are that stored volume uh, has the primary storage on premise, okay, and you have cache data backed up into S3, and then a cached volume is going to have your primary store in S3, and on-prem is going to be a cached kind of low, frequently accessed files for low latency access. Okay, and then tape gateway is probably not something you'll work with very often. It's really just used for archival of data in Glacier and to support existing legacy on-prem tape backup solutions. Okay. All right. So high availability for databases. So RDS can utilize multiple availability zones, and it can have replicas of your master RDS database instances being asynchronously replicated. You can use read replicas, which it's important to note are not necessarily secondary databases because they can't, do writes. They're just for read traffic to help offload some of that from like a primary database. You've got Amazon Aurora, which is similar to RDS, but it's going to be more fault tolerant than RDS because, like I've mentioned a few times in past lectures, it separates the compute and the storage layers. It can use read replicas, and it continuously replicates your data across three availability zones via something called the Quorum and Gossip protocol, which isn't something you really need to go into at all for this exam, so don't worry too much about that. But just know that Amazon Aurora is highly available. It replicates your data across three availability zones. Okay, so DynamoDB data is going to be replicated across three availability zones as well in a single region via synchronous replication. So that means pretty much at all times, across all AZs, your data is going to look the same. Whereas with asynchronous, there might be a little replication lag. You can have global tables by using multiple regions with multi-master read-write capability and eventual consistency. And of course, you can use on-demand backups and point-in-time recovery. So again, DynamoDB is designed to be highly available and fast pretty much all over the world to a basically unlimited scale. So that is how the common uh, database services that you're going to work with, right? RDS, Aurora, and DynamoDB can be utilized in regards to high availability. Okay. All right, so let's take another quick break, and then when we come back, we will come back and look at AWS architecture. All right, so let's take 5. All right, let's get back to it with our architecture. So, of course, we are testing to become solution architects, so we naturally want to talk a little bit about architecture. So, a well designed architecture is a decoupled architecture. And as opposed to a monolithic architecture, a decoupled one is going to have components that work independent of each other to accomplish a task. And what that means is that if one part of a monolithic architecture fails, it'll likely affect everything else due to dependencies being on that same physical server. Whereas a decoupled architecture, for example, has 5 separate servers and each server performs a specific function, as opposed to one server performing 5 functions. Okay, so think of your architectures as event driven, utilizing services such as SQS and SNS, which we are going to talk heavily about. Okay. All right, so step functions are something that's a little new to AWS, and you can kind of see the console and the designer here. of what that would look like if you go to start working with them, but it basically allows you to create interactive and complex systems with many features to support your workloads. And it leverages Lambda to run functions that are basically in four categories, okay? So you've got in parallel, in sequence, in retry, and if then, okay? So when you decouple an application into multiple components, again, each one is going to do a task independently, and a failure is not going to affect other components, okay? When queuing services are involved, like SQS, there are producers and consumers. So to kind of have a idea or a visual here of how that workflow would look like, say you have here, you have your component one, which is sending the message A over to this queue, okay? And now this message, because the way SQS is designed behind the scenes by AWS, this message is going to live on a few different servers, okay? And it's got what's called a visibility timeout clock, which is how long it's going to be before this message is able to be seen. Okay, and you should definitely go look up SQS terminologies. I'm a little rusty on those off the top of my head, um, but those timeouts are definitely going to be something that you'll want to at least be somewhat familiar with. But then you've got component two, right, which is here. Okay, this will be the consumer. It's going to retrieve message A from this queue, and then the visibility timeout period is going to start. Okay, and the visibility timeout period is going to be how long it could be, again, before this message gets seen and consumed. Okay, so once component 2 processes message A, so it grabs the message from this queue during this visibility timeout period, okay, what's going to happen when this message is processed, it's going to be deleted from the queue during that period so that it doesn't get sent to other components and you don't get repeated messages, okay? So in this case, once this message is retrieved, okay, by component 2, this 40-second timeout starts, okay? And then in this case, from the time where it was seen to the time this message was processed and consumed, it took 25 seconds. And since it's within those parameters, it then deletes the message from the queue, okay? And then if it doesn't get consumed within that time, then it doesn't get processed, and you can move it to what's called a dead letter queue, okay? So, like we kind of talked about, there's 5 basic steps in sending and processing a message that involves a producer, a queue, and a consumer, right? So the producer puts the message in a queue. So component 1, the producer puts the message in this queue over here, which is this cluster of servers. The consumer polls the queue to receive new messages. So component 2 would be the consumer. It polls this queue, and it sees, hey, message A, that's a new message, okay? And then once it receives that message, the visibility timeout is set and then started to, again, avoid duplicate consumption of messages. So that's how long, again, it has to see and consume and then process and delete this message. Okay, the consumer then sends the delete message request to the queue, right? So once component 2 gets this message A, it then tells the queue, like, hey, I got it, we're good, go ahead and delete that, okay? And then if the message is not deleted or processed, the visibility timeout expires, and the message can then be consumed again by either this component or maybe there's another component pulling this queue, or you can have it sent to a dead letter queue, maybe if it fails multiple times, okay? And a dead letter queue is useful if you want to analyze like failed messages to see kind of why they're failing, right? So queue polling, kind of mentioned that, but it's basically how a consumer listens and receives messages from a queue. And it can be either short or long polling. Okay, short polling is the default, and basically what this means is that the receive message request queries only a subset of servers for new messages. And then SQS is going to send the response right away, even if messages are not found. So basically, it will only query, let's say like this cluster of 4 servers, right? So obviously one of the downfalls of that is that if this message is only put on like these 3 servers, for example, then it may not find that message, okay? But long polling is going to send that receive message request to all servers for messages. And then SQS is only going to send a message if one is found or if that polling wait time expires. Okay, so with long polling, instead of just polling these 4 servers, you're going to poll all of these servers, which is why it's called long, because it could take a little bit longer, especially if you've got a lot of maybe consumers that are polling a lot of queues. Okay. So short polling, this is kind of important to remember because this has come up in a test before, but short polling occurs when the wait time seconds parameter of a receive message request is set to 0, right? So like we said up here, SQS is going to send that response right away, even if nothing's found. So that's why, the wait time seconds parameter of a receive message request is set to 0, right? Because it's going to take action right away, all right? So that is queue polling. And you can have queue types. I kind of mentioned the dead letter queue a little bit, but the main queues that you're actually going to be using are going to be either standard or FIFO. And standard is kind of the default, as the name may suggest, but it's got unlimited throughput. It's got at least once delivery, and it's going to do best effort ordering. Okay, so it can process up to 120,000 messages at once, so it's a lot of messages. But as you can see down here on the left, we have standard queuing. So in this queue, right, you've got 5 different messages. So you've got message 4, 3, 3, 5, 2, and 1. As you can see, they are kind of in the right order, right? Message 1 and 2 came in first, obviously, but then it sent 5, and then there's a duplicate 3, and then there's 4. So it's going to get, like it says, at least once delivery of all these messages, but they may come out of order and you may have some duplicates. Okay. But if you don't want to have that problem, and maybe you don't have as many messages, you can consider FIFO queuing, which is first in, first out. It has high throughput, so not necessarily unlimited. It's got exactly once processing and FIFO delivery, and it can only process 20,000 messages at once. So over here we have a FIFO queue, and as you can see, the messages are here in the order 1 through 5, and there's only one of each, so they're going to get delivered only one time in order. Okay. So that's the big difference between FIFO and standard. All right. Now, dead letter queues are messages that couldn't be processed for whatever reason after meeting that max receive count limit. And basically what you can do is you can utilize SNS to alert you when messages were put into the queue. So again, you could maybe see like, is there something off with the action that it's trying to perform, or some kind of parameter or something? But you could just do analysis and see why some of your messages can't be processed. All right. So dead letter queue is kind of like your troubleshooting queue. All right. Speaking of SNS, we've got a service called Simple Notification Service that works hand in hand with SQS, amongst other things, that can basically notify you of events that happen. If you did our billing lab in the first week, which hopefully you did, we set up an SNS alert to send you a notification if you spent a certain amount of money on your cloud computing environment and resources. But it's your go-to service for receiving notifications, right? You can do text or email and a few others, but those are kind of the most commonly used message delivery protocols. You've got 3 components, okay, which are publishers, topics, and subscribers. So topics are going to kind of sit in between publishers and subscribers, and they're going to contain the messages that need to get delivered. So a publisher is going to send messages to a specified topic, and then of course a subscriber is going to subscribe to a topic, and then they're going to receive messages that get published to that topic. So that's important to remember. Subscribers will only receive messages from topics that they are subscribed to. Okay. And then, like I mentioned, you can send out notifications with push notification. It's like text, HTTPS, email, SMS, or Lambda functions. Okay. All right, so streaming data is kind of in its own realm, but it's an interesting component of your architecture because it's what generally deals with real-time data, kind of coming in on the fly. All right, and whenever you need to like collect, process, and query data in either real time or near real time, start thinking of the Kinesis family. Okay, and I say Kinesis family because there's a few different services, kind of depending on the use case, but again, the kind of underlying theme here is that they help you with like real-time event notifications, data speed transfer, ingesting, a bunch of data, querying it in real time, whatever. But you've got Kinesis data streams, data firehose, data analytics, and video streams. Okay. So if you're not really too familiar with stream processing, that's totally fine. I personally haven't worked with it much either myself. But it's important to know that some data has value later, but some data is only valuable the moment that it is produced. Okay, and there's two main issues of traditional batch processing. Okay, which typically handles like large scale real time data. You have session states that are collections of related events, and they're split into sections that are processed at predictable intervals. The problem with this is that there could be overlap between those intervals, which makes analysis difficult because you may not know, what time something came in because you're jamming them into these intervals. And it's designed to wait, and again, until a specific amount of data is accumulated before processing starts. So there could be some delays as well, with your analysis and ingestion of data. Okay. Stream processing helps this by addressing the issues of latency and session boundaries and inconsistent load. And the goal of stream processing is to provide a reliable source for analytics from a single source of truth. So you kind of have like one centralized area that's processing your streams and analyzing it. So there's no lag or inconsistencies between like different batch processing jobs. Okay. Batch processing, may be better for data at rest, but data kind of in motion in real time, you want to start thinking of stream processing. Okay, so there's a few different components of stream processing, and uh, they are a producer, which is what collects events and transactions, and then just puts them into your data stream. Your data stream is what stores the data itself, and then your consumers are what's going to consume the data. So it's similar to like SNS, and that there's producers, consumers, but instead of topics, you have data streams. So streaming processing, really eliminates the need for large databases, and since each stream has its own data and state, it's decoupled, which again really helps us out with that decoupled architecture. Okay, that highly available decoupled architecture. All right. So Kinesis data stream, it also has a few layers. We've got a source, which is going to be what generates data, via maybe a mobile device, metering or logs or click streams or whatever. You've got the stream ingestion, which is going to be when the data is collected by one or more producers, so like SDKs or Kinesis agent, and then it's going to be formatted as data records and then actually put into the stream. Okay. You've got the stream data storage, which is going to store data for 24 hours, which is the default, but you could potentially store it for up to 365 days if you really needed to. And records can't be changed once they're stored, they can only be expired. Okay. So stream processing is going to be, of course, the consumers like Kinesis Data Analytics or Data Firehose that process the data inside of your streams. And then the destination is going to be, consumers then are going to send the data to whatever, such as like an S3 bucket, maybe a data warehouse, or maybe a data lake. The destination is generally going to be somewhere that can handle a lot of data that's potentially, very, very large in scale. And all three of those can definitely do that. Okay. So Which Kinesis service do you actually need is the $1 million question, because there's a few of them. So this is kind of an important slide, when we think about just like pure test preparation. So data streams are useful, or is useful, right? The data stream service is useful when you need to ingest, process, and then transfer data to a destination. It's going to require configuring shards and producers. Okay. Data Firehose is useful if you are more concerned about sending data straight to a destination like S3 or Redshift or a data lake or whatever. So, you're not sitting there trying to like process it and everything. You just want to send it straight to a destination. You don't need to write any applications like producers to manage the process. And because it's designed to just send things straight to a destination, it's only going to store data for up to 24 hours. Okay. It's going to assume by then you'll have sent it to wherever you're actually going to want to store it and deal with it. Data analytics, as the name suggests, uses SQL to query and analyze data in a stream or a fire hose up to real time. And then, just like with Athena and other SQL queries, you could store your results in a destination like S3. And then video streams, as you might have guessed, is useful for streaming video, but it can also, handle any other binary encoded data as opposed to the other three that just use base64 text encoded data. Okay. All right. So Amazon EMR, Elastic MapReduce, is designed to process and analyze vast amounts of data by using jobs that can be short or long running. It's going to be based on Apache Hadoop framework, which is kind of it's the standard, one of the standards for big data processing that's configured on like abstracted EC2 instances that run the workloads that you won't ever have to, deal with or configure. It's used for things such as log analytics, data warehousing, machine learning, financial analyzing, and or web indexing. Okay. So Amazon MSK is a managed streaming for Apache Kafka. Lets you run apps that utilize Apache Kafka. I haven't really worked with this much. I don't really use Kafka as much, but a use case would be needing a solution to intake data with extreme fault tolerance, allowing for a stream of records that preserves the integrity of the data, including the order it was received. So if you need to intake a stream of data and preserve the order it was received, this is something you would want to consider. And it works on a publisher subscriber model where Kafka ingests data from a producer and then publishes it to subscribers on a FIFO basis. So, of course, it uses producers as the publishers, topics as the middleman, and then subscribers as the consumers. Okay. So you've got a few different just kind of services that you'll want to be broadly familiar with. Definitely don't need to know the fine details of these, but it's important to know they exist because they're considered fair game on the exam. You've got AWS Device Farm, which lets you test and interact with your app on devices at once, like maybe Android, iOS, or Windows, and reproduce issues in real time. And that basically just helps you find issues with your applications on different platforms before your customers do. Okay. Amazon Pinpoint Service is designed to run target campaigns to drive user engagement in mobile apps. It's useful to help marketers send the right data to the right customers at the right time. Yeah. And then AWS Amplify helps front-end developers build and host full-stack applications on AWS. ML services, so SageMaker, it's going to be the service that provides pretty much all the tools you need to deploy and train ML models. It's the primary ML service. Amazon Comprehend uses pre-trained models to extract insights from within text documents. You could use it to maybe analyze like customer sentiment from product reviews. And then Forecast is something that uses machine learning to deliver accurate forecasts for time series data sets, like monthly sales of a product or just weekly website traffic. Okay. So there's, of course, multiple benefits to multi-tier architectures. But when you use multi-tier architectures, you can potentially utilize serverless technologies. And this is going to increase your fault tolerance and availability for your applications. And generally, your applications are going to need 3 layers. And more or less what it'll look like is the presentation layer, which is what your end user is going to see, like maybe on their phone or their computer or whatever. And then logic is going to be what processes application logic. So maybe what handles like authentication and user requests, things of that nature. And then of course your data tier is going to be what stores your data, as you might guess, right? It's going to have all your connectors, your routers, and everything data related. Okay. So let's go ahead. So it's been about an hour. And normally we would take a longer break right now, but I'm pretty sure we can finish the rest of this in another 15-minute stretch. So let's just go ahead and take 5 real quick. Grab some water, grab bathroom, whatever. And then when we come back, we are going to just kind of go through this and go ahead and finish up this section and get on with our lives. All right, so let's go ahead and take 5. Set real quick here. All right. A little shorter break, but we'll make it happen. All right, grab a sip. All right, so serverless. Serverless is AWS and just cloud computing providers in general love talking about serverless, okay? And for good reason. I mean, it's a huge component of cloud computing that allows you to do, a ton of things based on specific use cases, which, are actually pretty common. But in general, serverless applications are highly available and resilient. And again, basically, what that means is that when we talk about serverless, we're our application, our workloads aren't tied to one physical server, and if something were to happen, we'd be screwed. Okay, what it means is that our servers, our applications are running on a server. Okay, and if something were to happen to that server, well, we could automatically switch it to another server, right? So we're not tied to one box particularly. All right. You can have serverless compute, storage, and app integration, and those are some examples there of some serverless services you can use. And if you want to forego server responsibility, so like the maintenance of a server, updates, all the things required with maintaining a server, consider serverless. If you want to run functions, but you don't want to pay for idle servers that you have set up or provisioned, consider serverless. And if you have workload demands that are unpredictable or you need to run multiple concurrent versions of your functions, consider serverless, right? So maybe like you have batch workloads that kind of start and stop or whenever, and you can run them on like serverless spot instances, okay? All right, so serverless design patterns. So just a few kind of cases here, examples rather, of what we could do with serverless. So up here, say we have some users, and those users are connecting to a S3 bucket that we are using to statically host our website. But if you'll remember, S3 gets replicated across multiple availability zones, so it's not tied to one specific server that's in one availability zone in one data center on one rack. Okay, you could use Cognito, which is a serverless identity, kind of federated identity service to validate access to the website, on your bucket from your users. And then you could use, API gateway and Lambda to maybe write some information to a Dynamo database table. And then what's going to happen is you're going to use a fan out, an application that's going to take in a stream from DynamoDB, and it's going to fan out events using Lambda to an event bus. And then the event bus is going to then send those streams directly to an S3 bucket via Firehose. Remember, Firehose is the service you use if you want to just immediately send data or events to a destination. In this case, is a bucket. And then as an administrator, you could use Athena, which is a serverless SQL-like service to query data in your S3 bucket. Okay. And then as an operator, maybe someone who's working with the company, maybe like a DevOps person, whatever. You can utilize CloudWatch to set up alarms that take action based on events that are detected from dashboard or maybe like certain metrics. And so all this entire application, this entire setup can be done completely serverless, right? You don't need a physical box to make any of this work, right? Which is, again, one of the great value adds of AWS. You could have applications, services, whatever, that are completely serverless and are highly available and very fault tolerant because they're not tied to a specific box, all right? So, like I mentioned, you've got some options for different kind of categories of services, but you've got compute, which we kind of already know what compute's used for, like running websites or big data analytics. And you could use Lambda or Fargate in the realm of compute. You've got application integration, which allows you to connect to and send data to AWS and your other applications. And then you've got EventBridge, which allows you to react based off of, as we could see here, events from what are called event buses that you designate to have sources. You've got step functions, which we looked at earlier, SQS, SNS, API gateway, and app sync. Okay. So storage, it just serverless helps make your storage more reliable and resilient. And you can use S3, DynamoDB, and Aurora serverless as some options there. Okay. And DynamoDB, you might be wondering, like, I thought that was a database service. It's kind of blurry on you because it's very dynamic service. AWS, technically they consider it a database service. I mean, obviously they've got DB in the name, DynamoDB. But you can potentially use it for storage as well, maybe for like snapshots and backups, things of that nature. Okay. All right, so migration strategies. So it's important to understand, conceptually how to migrate either into the cloud or out of the cloud, because that's what most companies are going to do, right? I mentioned earlier that a lot of companies, aren't really cloud native and they aren't really 100% on-prem. There's some combination of cloud, some combination of on-prem, okay? And when you have that hybrid architecture, sometimes you need to take data, in and out, or resources in and out of the cloud, okay? But generally, a migration is going to have three stages, okay? You're going to have the assessment stage where you determine how ready your organization is to migrate to AWS. You're going to set goals and objectives and present the business use case, like why, in this case, we would be going into the cloud for, say, our storage. And after you kind of get an idea of where you're at and how ready you are, if there's anything you kind of need to set in place, then you move into the mobilization stage, which really kind of starts to hammer out the details of your migration. So you get a more granular analysis of kind of the planning and the strategy you're going to take to migrate into the cloud. And what you're going to do is you're going to define migration strategies such as relocating, rehosting, refactoring, repurchasing, whatever, because there are going to be some changes that you make to your architecture if you're migrating into the cloud. So you need to kind of consider all the components that go into that are still going to allow your application to function as intended. And then you're going to identify skill gaps in your organization. So, for example, if you have a DBA on-prem and you say, hey, we're going into AWS, and he says, what's that? Well, that's a skill gap, and you're going to need to train him up on what the cloud actually is and why you're doing what you're doing, and maybe give him some background on some cloud-based technologies that he actually works with. Okay, and then once you've kind of moved past that stage, it's time to actually do the thing. So you're going to move into the migrate and modernize stage, which is where you design your deployments and your solutions. Okay, you know what you're going to do. Now it's time to actually design them. You are going to need to identify dependencies and understand connectivity requirements between AWS services. And you're going to want to validate your designs. So just make sure everything is all set, ready to go. And then, you're ideally going to maybe pick an off time where people aren't on your network, people aren't using your resources, and you're going to push the button and you're going to migrate. And then you're going to pray that it turns out as expected. But if it doesn't, there's things you can do to kind of capture logs and figure out what's going on. But, the more granular you get with your analysis and your plan, the better your odds are going to be of a successful migration. Okay. And modernization basically just means, like, say, you're on like a legacy database on-prem, for example. Maybe you need to, when you migrate, upgrade to a more modern database engine. Okay. So just bringing things up to speed to meet your business requirement. All right. So AWS Migration Evaluator is kind of a helpful 10,000 foot view service. So just a high level overview of what your migration would look like. It's going to provide a mechanism to help you get a baseline of your on-prem environment. And it's going to project costs that are going to use cost modeling and data analysis from some information that you provide of your on-prem environment. And then it's going to send that data to Quick Insight reports, or to Migration Hub, so you can then kind of share your findings with others, because it's probably going to be required, right? You're not the only one that is affected by migration. So Quick Insight reports are concise summaries that show cost analysis and data usage patterns. Again, it's helpful to build business value for moving to the cloud, so you can send these reports to like maybe executives, shareholders, other departments, whatever. And then the Migration Hub is going to provide the dashboard view of your migration project. It's kind of like the central brain of your migration, and it will help you discover and migrate existing services that may be in different locations. Okay, so it's kind of like the centralized hub to manage your migration from start to finish. Okay. So the mobilization, you have a couple options. You can use the application discovery service, which dives deep into your current workloads to get more information, such as performance metrics, data usage, and configuration. You can use the agent-based discovery, which is installed on your servers, either Windows or Linux, and then you're going to connect to the app discovery service. Okay, so it uses an agent similar to like maybe a CloudWatch agent or something like that that's going to be installed on your servers. Uh, you could also use agentless discovery, which is only available for VMware VMs, and it's going to connect to ADS kind of the same way that an agent would after it collects data. All right. And then you have AWS Control Tower, which is very useful when you have maybe multiple accounts that are involved. For example, utilizing AWS organizations. It's going to be based on blueprints, which configure access security and just your overall account structure. So maybe like, with organizations, some SCPs as well. Okay. All right. So migration M&M. So the modernization and mobilization. So for server, database, and app migration, you've got the AWS App Migration Service, Database Migration Service, and the AWS Service Catalog. For data migration, you've got the AWS Transfer family, you've got Data Sync, and you've got the Storage Gateway or Snowball Edge if you need like physical devices because maybe you have terabytes of data. All right. So let's take a breath here. I feel like I'm talking fast. I promised you we would finish this soon, and as you can see, we are. I think this summary is only like 1 or 2 slides. But a decoupled architecture should ultimately be your primary goal. It's more resilient, more available. It just really fully kind of takes advantage of what cloud computing has to offer. Okay. SQS and SNS are going to be 2 key components that help you decouple your architecture. And as we saw in that one graphic, we have 4 types of disaster recovery methods. We've got backup and restore, which is the slowest to full recovery, but the cheapest by far. You've got the pilot light, which is a extremely scaled down and shut down copy of your core services. So like maybe one thing, maybe like a database, for example, or some instances. And then you've got a warm standby, which is the same as Pilot Light, but you're going to have scaled down, components of your architecture that are running, but you're not actually routing traffic to them. And then you've got multi-site active-active, which is basically just like mirror images of production workload. It's the most expensive, but you're going to have pretty much no downtime. Okay. The Kinesis family is what you should start thinking of if we're talking streaming and real-time data processing. And serverless is helpful if you have, a requirement for high availability and resiliency, and or unpredictable workloads. Okay. Uh, as I mentioned a few times, most companies will have a hybrid architecture, and you will be asked about migration on the test. So it's important to understand migration strategies and the services involved. So you've got the assessment stage, the mobilization stage, and then finally M&M, the migration and modernization stage. All right. Each of those have their own kind of umbrella of services that are helpful. So definitely kind of know what those are from a 10,000-foot view. But obviously, you don't need to know the details and the ins and outs of implementing an actual migration. Okay, not yet, anyways. Maybe on the professional. All right. All right. So we made it. It was an hour and 21 minutes, so we almost made it within the promised time. But, high availability and the architecture are definitely important sections because we're studying to be architects. So we need to know how to design things to be, met with, high regard in terms of being able to meet SLAs, being able to be there when we need it. So that is high availability and architecture in a nutshell. Be sure to do the labs. There's actually quite a few this week. that will be tremendously helpful for you in this domain. And we will see you next week.